Chapter 4, Section 2.
So in this section, we're going to cover the number e, a very, very important number in math, in calculus, in just about everything in our lives, really. A lot of stuff. Like, there's a few things in math that are kind of niche and don't really impact our lives in many ways, but e is definitely a very, very impactful development in math. It has far-reaching implications, and it's really knitted into our fabric of science in a lot of different ways. So it is really, really important. We're going to look at the natural exponential function and then continuously compound interest. So first off, e. What is e? How do we get to e? Let's consider e. Okay, so any positive number can be used as a base for an exponential function, right? Going back to the formula for an exponential function. Remember that the formula we were looking at was just, say, f of t. Why is this thing in the most thick? Okay, f of t equals to some base a to the power of t, right? Akin to f of x equal to a to the x power, where a was the base, and it could be any number that was strictly bigger than 0, right, to infinity. However, we also skip the number 1, and we skip it just because it's boring to have 1 to the x power. Okay, but it could be any real number at all, right? That's what they're referring to here, and they say that any positive number except 1 is considered to be the base of t, the base of this exponential function. Okay, so we're going to consider, how about if we let that base be the number e? So before that, let's consider what is e and how do we get e. Here is e. E comes from, well, there's a few different ways to develop the number e, but here's one of them. It starts off by thinking about what happens with this function right here. So if we think about the function, say consider the function f of n, right? So the input is n. F of n equal to 1 plus 1 over n raised to the nth power, right? So that's a function we're going to think about. Some brilliant person long ago was sitting around on a Saturday night thinking about this function, right? What else do you have to do? What better thing to do is there to sit around thinking about interesting functions? So he thought about this one, raise the power of n. So let's say n was equal to 1. Then that means that this would turn into 1 plus 1 over 1 raised to the 1 power. Good. So that would just be 2 to the power of 1. So then the first number is just 2. Good. Okay, what if n was 2? N was 2. Then we would have 1 plus 1 over 2 raised to the 2 power. 1 plus 1/2 is 1.5, which is 3 over 2. Raised to the second power, which makes it 9 over 4. 4 goes into 9 2 times. What the heck is that? 9 over 4, which gives you 2 1/4, or 2.25. Okay, so that's the value we get when n equals to 2. Let's do one more. 3. What if n was 3? Okay, so we have 1 plus 1 over 3 raised to the third power. Okay, so this is going to be 4/3. That goes into it 1, and then 1 remaining makes it 1 1/3, which is what this is. Raise the power of 3, which makes it 4 to the third power is 64, and 3 to the third power is 27, which makes it, okay, this time I'll reach up for a calculator. 64 divided by 27 is going to be 2.37, 2.37037, and so on and so forth. So it's really 037 barred. Okay, and then we would keep going, right? What happens when n equals to 4, and what happens when n equals to 5, and what happens when n equals to 6, right? So we got to keep going, dot, 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 dot. And what we want to explore is what happens as this n value goes down, down, and down, goes toward infinity. That's the pattern we're looking for, okay? It's kind of hard to see initially, so you really have to think about big numbers going forward is what we want to look at. So let's use Excel to try and see where that goes, and hopefully my computer can handle that. If not, we'll skip it, but let's see. So I'm just going to use Excel to repeat that little table I had just created, exact same thing. I'm just going to put it on here so that we can do it faster. So we have a column that's going to be the n values, like 1 and 2 and 3, for example. Right? And then we have this other column, which is the actual function, and it was going to be 1 plus 1 divided by n right? And then the whole thing is raised to the power of n. Okay, so this is the equation now. F of n equals to 1 plus parentheses 1 divided by whatever's in this box, close parentheses, to the power of whatever's in this box. Correction, no, go away. Okay, go away. So I want to raise the whole thing to the power of that guy. That should fix it. There we go. Okay, so that's the same answer we got for the first one. And then here are the first three that we got. Let me make this bigger. Let's say we go out to about, that's not a good sign. It's already slow. That's definitely not a good sign. Okay, so we'll just do it for a little while and see how far this goes. Okay, so let's make this equal to the previous number plus 1. And then this number is going to be equal to that number. And then these two are that. Okay, so here are the first three numbers, just like we did it in our table. But now the system is set up so that I can just expand this a little bit more. And now I automatically get what happens when n equals to 4. When n equals to 4, we plug it in here. We end up with 1 plus 1/4 raised to the 4th power. And then we end up with 2.44. Okay, and then we keep going. How about if we do it to the 5th power? That's going to be that one. And what if we do it to the 6th power and to the 7th power, okay? But again, we care about very large numbers. So let me skip on down and do this for a lot of numbers. I hope my computer doesn't crash. Okay, so keeping track of the value of n, look at what happens to the output, right? Obviously, we always start off with a 2, but then the first decimal after the 2, the first decimal was a 2 first, then a 3, then a 4, then a 5. So let's keep track of that first decimal after the 2. Right now it's at 6, 2.6 something. And then it says 7 now, 2.7 something. So what happens with this formula is that it's always growing. It's growing, 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 always growing. However, the speed at which it grows begins to slow down. And so as we go farther and farther out, the first few digits become more and more stable. Right? Obviously, we always start off with a 2. And then the first decimal value after the 2 is eventually centers into a 7. And then it doesn't change after that. And then after a while, the 1 becomes pretty constant after the 7. So it's always 2.71 something. And it looks extra weird because sometimes it changes values. But anyway, so then after the 1, there's a 6 at the moment. And if we keep going through this, eventually that might change. Okay, so this is, I'm going to stop here. This is after n equals to 774. The first couple of decimal places are already pretty constant, right? It's always 2.71 something, 2.71 something. And if we keep going way, way, way down here, eventually we might see, look, it's about to change from a 6. It's getting really close to change from a 6 to a 7. So now it's 2.717. Okay, so that 7 wasn't quite so stable. But if we keep going, where is this heading? Now, this looks a little weird because sometimes we have more decimal places, sometimes we have less decimal places. Let's make a couple of changes up here. First of all, let's set this, let me set it to a specific number of decimal places. Where's the, on that side. Ah, shoot, that's not what I wanted. On that side. I want it to be a number with 30 decimal places. And let's extend that to here. Okay, so, the computer quits after a while. So there's going to be a lot of zeros at the end, not because it really is zeros at the end, but because the computer, not necessarily because it's zeros at the end, but because it's more likely that the computer just doesn't have that much computing power to go out to that many decimal places. But at least this way it'll be a little bit more consistent. And also, I want n to go really big. So instead of jumping by ones every time, I'm gonna change this so we're actually jumping by hundreds every time. Let's do that. So let's see, can I extend this up? Oh, I didn't like that. Can I extend this thing up? Yeah, that works. Okay, so let's change this so that it changes by 100 values every time. right? So I went from 100 to 101, and then I want to go to 201, to 301, to 401. So I'm going to be jumping by hundreds. That way I really let n get really big really quickly. And now let's extend this out. Not too much, since my computer doesn't go that far out. All right, hopefully that's catch up. Okay, so now we see that n is really growing quickly. If we jump to n equals to 101, this would be 1 plus 1 over 101 raised to the power of 101. And then here, this is the case where n is 501. 1 plus 1 over 501 raised to the power of 501. Now we can really see what happens to the outputs, right? So obviously we start off with a 2, and that first whole number value is always 2. That doesn't change. The first value after the 2 pretty quickly locks in on 7. Remember when we were doing 1, 2, 3, 4, 5, it didn't lock in on 7 right away. But now, since we're jumping by hundreds, we can see that that first decimal place is pretty much locked in. Okay, so as we let n grow bigger and bigger and bigger, we see that the first few decimal places are pretty locked in. It's always a 2.71. The 1 is already locked in. The 8 looks pretty locked in at this point. The number after the 8 right now is a 2. And that one, at the moment, seems a little stable, but the one right after that is still changing pretty quickly, right? So the 4th, 5th decimal place at this point are still pretty actively moving. And remember that as n gets bigger and bigger and bigger, this will always be growing, but it keeps growing at a smaller and smaller amount. So the further out we go, the more we lock in on some value. Okay, so the point of all this is that we wanted to study what happens as this function goes out to infinity. Where does this head? And it heads to the value we call e. Okay, so eventually that 2 that's after the 8 will lock in on a 3. So it'll be 2.7183, and then dot, 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 dot after that. So e is what we call an irrational number. It's a number that goes on to infinity and never repeats itself. There's no pattern to its repetition. If we kept going through this, if we had a really powerful computer and really went to town on this and really pushed a very, very high value of n, we would get an even better approximation of what e is. But of course, we would never get the complete approximation. The complete exact answer. But if we kept going, eventually we would see, here's a little table similar to it. So here's a table similar to what I created. At 1, we had a 2. At 5, we get this decimal. At 10, this decimal. At 100, that decimal, and so on and so forth. But eventually it starts to narrow down on this. Oh, and I was wrong. This doesn't move to 3. It stays at a 2. And then the next decimal place that kind of locks in is an 8. Okay, so we got to keep going, though. This is not e either. There's no way to actually write down e. We just got to keep going, right? And if we kept going, we get more and more and more decimal places of accuracy. This is when n equals to 1,000,000, we get this number. So if we let n grow even bigger, we'll end up with an even better approximation. Good. There are kind of contests in the math world for people to figure out a larger approximation to this. So if you build a computer that is purely dedicated to do what I just did with Excel, and then really push the outer limits, then you can win this contest. So I believe that at the moment, again, this is something you can Google, I think at the moment they're in the like 50 billion decimals kind of area for the winner. So this one is accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? This is accurate to 20 decimal places. The current winner of who's been the most accurate, I think they're in like 50 billion decimals area. I could be wrong, but yeah, Google it. It's pretty interesting. I mean, I'm sure they must have created a computer purely dedicated for this and had it running for like months, I'm sure, in order to reach those high levels of specificity. But for us, we don't need that much accuracy. It's good to know the concept of how we get it, right? It's this number that we can't really write down the actual exact number, but we can be as accurate as we want, depending on how many n values you want to use. For us, we normally are fine with 3 or 4 decimal places of accuracy for the most part. But if you really want to get more accurate, then you can get more decimal places of e. You can get as many as you want, depending on the value of n. Good? Any questions at all? No. I still haven't answered why we care about this. This was just fun for now, obviously. But why do we care about this? Why is this such an important thing? That's to be discovered. It is a very important number. Okay, the number e is based on the natural exponential function. Why use such a strange base for an exponential function? It might seem at first a base such as 10 is easier to work with, right? Base 10 is easy to work with because we have a base 10 number system is what we're used to, right? We have a base 10 number system. You know, why do we have a base 10 number system? Because it takes 10 unique little figures to make up our numbers, right? We've created them with 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 0 is the other one right back here. There are 10 of them. If we count these, there are 10 of them. And then all other numbers are created by combining these in one way or the other, and where the order matters, right? 4, 5, 6 is 456, 6, 5, 4 is 654, right? So we recombine these, and the length makes a difference, and the order makes a difference, and we toss in the decimal place and commas, and we can express any real number, any rational number that we want to express, right? So we use base 10. I know that we're all incredibly comfortable with these. We've seen them all our lives, so it almost seems like second nature that, of course, there's 10 of them. But, you know, if I was going to invent my own number system, maybe I decide to make it base 4. Maybe I decide this is one number, and then this is two numbers, and then maybe this is another number, and maybe this is another number, right? Maybe it's base 4, and then all my numbers would be based on this, including the order, right? So the next one on my list might be, you know, if I was creating my numbers, the next one on the list, instead of coming up with a brand new picture to describe the next one, I might just recombine these in some order, right? Next, you have to get the one with the X like that, and this one, and that's the next number on my list. And the next number after that, maybe it's, I don't know, maybe it's this one, again, repeated, and then this weird, maybe this one with this one, 2 dots on there. Right? Maybe this is my next number. I don't know, right? I could keep going. But some way of reorganizing and recombining my original 4 numbers, these original 4, if I kept going, and the reordering of them and maybe tossing in a decimal would allow me to come up with all numbers, then this would be a base 4 number system. But we have a base 10 number system. And so because we have a base 10 number system, 10 is often full of really great outcomes. And why does this thing keep popping up? So it's really convenient to do things in power 10. Wait. Scientific notation, for example, is very useful for that reason. Anyway, but now, out of nowhere, we're suggesting that this value e is just as useful, just as important, and we will see why. Right? It comes up a lot in calculus, and it's really fundamental to a big part of calculus, so it's really important. So we're allowed to have any base, so we're going to let e be the base. Right? So when you see this, mentally you can think of converting it to its decimal approximation. Remember that e is approximately 2.7183 is usually rounded to that, approximately. And these little wiggly equal signs means that it's approximate. So when you see this, you're really being asked, really being asked this. It's 2.7183 to the power of x. Right? So think of it as any other base number raised to an exponent. Okay, so let's compare it to other functions. Remember that the graph of any exponential function where the base is bigger than 1 is going to have this sort of shape. For x values that are greater than 0, it's going to grow up toward infinity. And for base numbers that are less than 0, negative values, it's going to grow down or push down toward 0. Let's use Desmos to demonstrate that. So remember that if we have y equals to 2 to the power of x, we have this kind of a shape, this kind of a graph. It goes through the point 0, 1, because 2 to the 0 power is still 1. And then if we let x be a 1, we have a 2. So it goes through the point 1, 2, right in here. Right in, come on, get in there. There it is, 1, 2. Good. And then if we let x equal to 2, then we get the point 2, 4, which is right in there. Good. On the other hand, if we let x equal to -2, the negative flips it upside down, and so we end up getting 1 over 2 to the power of 2, which is equal to 1/4. That'll give us this number right here. When x equals to -2, we get 1/4 as the output, or 0.25. Is that okay? Any questions about that? Okay, so we saw that whenever y has a base that's bigger than 1, we're going to get this same shape. So if y was equal to, I don't know, how about 5 to the power of x, then it has the same sort of shape, except that for the positive numbers, it'll grow to infinity a little bit faster. And for negative numbers, it'll grow towards 0 a little bit faster. So that's what happens with that base values. We let it be some sort of slider. Let's let that be a. A is a slider. And let's let it be equal to 0.1 to, I don't know, 10 by 0.1 numbers. And so here's 2, here's 2. So when a equals to 2, we have that 2 to the x power. And as it gets bigger, so here it is when a equals to 3, it has that shape. When a equals to 4, it has that shape. When a equals to 5, 6, 7, 8, 9, 10, right? So it gets bigger and bigger and bigger and bigger and bigger. And then the shape, it stays the same shape. It always goes through the point 0, 1. And then the same pattern occurs that on the positive end of the domain, it'll grow toward infinity faster and faster, the bigger the base. And on the negative side of the domain, it'll grow towards 0 faster and faster. Note that the output is never equal to a negative number. Right? The output is always positive. And the output is never actually equal to 0 either. It gets infinitely close to 0, but never actually 0. Good. Okay, so I get to punch in whatever number I want as the base. Here I'm going by multiples of 0.1 and skipping through these values. But it can be anything. So I can make it be equal to 2.7183, the value of e, to get a pretty good approximation. So when y equals to 3, y equals to 3 to the x power, we get that purple one. So we know that the one we're looking for is going to be somewhere in between those, right? Because e is somewhere between 2 and 3. So it's equals to e to the power of x. Oops, the power of x. So it's this black one right here is the one we want, right? The red one is 2 to the x power. The purple one is 3 to the x power. And as you can see, the black one on here would be e to the x power. It has the same shape. And if we want to create a table, we can find all those same values that way. So let's, for example, create a table. Oops. X and e to the x power. Okay, so at 0, we're still going to get 1. Still goes through that. And at 1, that would be e to the 1 power. That's just e, 2.718. Good. When we have 2, then we'll have 2.718 squared, which turns out to be 7.38. Okay, and that's what this little dot right here is. Okay. When we let this be 3, then it's going to be 3 squared, which is going to give us all the way out to 20-something. So that's going to be over here. Here it is. 3, 20.086. Here is 2, 7.389. Here is 1, 2.78, and then 0, 1. And then, of course, if we let n equal to -1, we'll get 1 over e, which then gives you approximately this value, 0.3678, which will be like that guy right in there. Good. So slowly we get to see the shape of the graph of e to the x power. Any questions? No? Good? Sort of? Kind of? Again, we still haven't explained why it's so important, but it is. We'll get to why it's so important in a little bit. Okay, some expressions. So evaluate each expression, round it to 5 decimal places, and the intention here is to use your calculator. So just to make sure you know how to use your calculator. So let's use the calculator. Can I already have it open? Oh, thought I did. So we have a special magical button on our calculator that's E, because it's really important. So rather than typing in the approximation, 2.7, we can just use the value E, the number on our calculator. And the E button is right above the division button, right there. The little E. Okay, so if we type in second and then that button, and we get the little E, and if we hit enter, we'll get the actual number, 2.718281828. And then this is just what is being displayed. I believe the calculator internally has it out to more decimal places than this. So this would give you a very nice, very, very close approximation to your outputs. So let's do the first one, which is E to the power of 3. So there's our answer to the first one. E to the power of 3 should be 20.085536, that guy. Good. The next one, let's put 2 times, and I'm going to put it in parentheses, E to the power of, and then it's negative 0.53, and then close parentheses. and enter. So I get that guy. It's such an important value, e, that they also gave you a second shortcut for e. Here I'm kind of manually putting e to the power of, but they also gave you the function e to the power of, which is over here. So we can also use that one, right? So we can hit second, and then this guy, and that automatically skips the one button that says to the power of. So I don't know how much of a shortcut it is, but it's a bit of a shortcut. So we can just put 3 there, hit enter, we get the same answer. Or second, and then e to the x, and then put in negative 0.53. Right, we get an answer, and then we want to multiply that answer times 2 to finish out our thing. So we can hit 2 times, and now you can manually type in 0.5886. You can do that. Or we can use this button here that says answer, and that'll be the previous answer recorded on your calculator. So hit second, answer, and then it'll automatically be 2 times this result there. So we get that. Good. And finally, we had second, oops, here. We had e to the 4.8. Any questions on how to use your calculator to approximate these values? No? Nobody? Nobody? Good. So same results we got from my calculator. Any questions, any questions, any questions, any questions? Okay, one of the reasons e is so important is because it appears a lot in nature. One of the important aspects of math, one of the reasons we study math, is because it helps us understand the world around us, right? So there's a big application part of math. It's not the entirety of math. It's just one facet of it. We're trying to understand how gravity works. We're trying to understand how genetics works and how air around the surface of a wing functions, and all these things that we're trying to understand. And we can come up with mathematical models that either exactly explain how it works or give us a pretty good approximation. And so when we're trying to come up with these models, these explanations for how the universe works, often we find that this special number e becomes very useful in either giving us the exact model, the exact equation that describes exactly how it works, or at least a very good approximation. An approximation that is so good that it is almost equivalent to knowing the answer itself, right? When you're trying to understand the flow of air around a wing, it would be great to understand an exact equation that that definitely tells you exactly what the answer is. But if you come up with an equation that is good to 30 decimal places, that's probably good enough, right? So the area of math is pretty big, pretty diverse, but the applied math part of it usually focuses itself on coming up with mathematics that helps us define the world around us. The other side, that's more theoretical math, doesn't necessarily care too much about that. The other reason we study math is because it helps us become rational thinkers, good puzzle solvers, and we have found, over the course of public education, that it's a really good way to get people to become better puzzle solvers, good rational thinkers, to be able to apply that sort of thinking to other areas in their lives. So it's something we push for that reason. Everyone should learn math for that reason. But then there's also this applied side. Okay, so here's an example. When we try and describe how viruses flow through a population, the number e appears in the models that do a pretty good job of describing it. So here is a case. An infectious disease begins to spread in a small city of a population of 10,000. After T days, the number of people who have succumbed to the virus is modeled by this function, right? So V of T is going to be the number of people who have succumbed to the virus after T number of days. So here is the entire population, and here is this thing here. So let's look at the first case. How many infected people are there initially at time t equals to 0? So this is a pretty easy example, really, where all we have to do is plug in, or this is a plug and chug question. Unfortunately, it's not more interesting than that, but we'll try and come up with examples that are a little more interesting. Okay, so this one's just a plug and chug. So all we have to do is replace that t value with a 1, and so we get this, 12, 4, 5 times e to the power of negative 0.97. And then we want to know what happens when this is a 0. And t equals to 0, so we multiply this by 0. Okay, so if we multiply this one by 0, then that means that whole thing is going to be 0. And e to the power of 0 is 1. Good. So then 1 times 1245 is 1245. And 1245 plus 5 is just going to be 1250. So this one ends up being 10,000 divided by 1250, which ends up being 10,000 gives you 8. Good. So according to this model, this is saying that at time equals to 0, at the very beginning, there are 8 infected people in this population of 10,000. And then, of course, they're going to begin to infect others, and then the people they infect others, and so it begins to grow exponentially, right? It's a pretty popular phrase, exponential growth. Okay, find the number of affected people after 1 day, after 2 days, after 5 days. Okay, so all we have to do is replace this 0 value with a 1 to see what happens after 1 day. Replace this 0 value with a 5 to see what happens after 5 days, and so on and so forth. So let's just see like a table of that. I think it's down here. Here's our solution. So we replace it with a 0, and we get an 8. And then we can use a calculator to find the rest of the answer. So here's a table for that. And remember, the formula for this whole thing was V of t equaled to 10,000 divided by 5 plus 1245 times e to the power of negative 0.9, what is it? Negative 0.97. T. Okay, so if we replace the t with a 1, we'll get this number. Replace the t with a 2, we'll get this number. Replace it with a 5, we'll get this number right here. So let's use a calculator. It says using a calculator to evaluate all these things. So let's practice doing that into our calculator. And we're going to do it by, well, obviously we can just type it all in. You know, when some of you are very new with these calculators, so I would recommend that we start off with the denominator, figure out the most complicated part, which is this, and kind of peel it away from the inside out, figure out what this is, and then times this, and then add 5, and then 10,000 divided by whatever answer you get in there. So let's just do it for 5, for example. So V of 5 is going to be 10,000 divided by 5 plus, don't worry about that, 18, 5 plus 1245 times e to the power of negative 0.97 times, and so we're going to do 5 and 5. And so we definitely want to use technology here. This arithmetic is pretty ugly, so please don't be afraid of technology. All right, so let's get over here, this thing. Okay, so to unravel this whole thing, let's put it over here. To unravel this whole thing, I'm going to start off with the exponential part of it. So clear. I'm going to start off with e to the power of, and then this product, which will be negative 0.97 times 5. And I'll get an answer from there. And then I want to multiply that answer. So now if you just jump ahead, another little shortcut, if you just jump ahead to the operation symbol first, it'll automatically assume that you mean the previous answer operation. So I could hit previous answer, like we did before, times, or something like that, times 7 or something. In this case, times 1245. Or I can just hit times, and it'll automatically assume that I mean the previous number, the previous result from our calculator. So that would be e to the power of this, and I want to multiply it by 1245, get an answer. And then again, I'm going to jump to the operation, plus, and it automatically assumes it's the previous number, plus 5. And then again, I'm going to do 10,000, 1, 2, 3, 4, 10,000 divided by the previous number, second answer, enter, and I get 678.13, right, approximately. Remember, this is a model, it won't be exactly the same. 678.13, okay, 678, approximately the same answer that we get from here. No. Okay, and then finally, let's do a graph for these, and you can do a graph on your calculator. If you do a graph on your calculator, then you're going to go over here, y equals, and then type it into here. You know, it's not so easy. You have to be really careful about parentheses and all that when you type in this whole thing. And of course, your calculator is going to do it in terms of x, not in terms of t, since every function in your calculator will be in terms of x. So just make sure you type it in all, and be careful with all the parentheses. So 10,000 divided by parentheses 5 plus parentheses and then the 1245 times, and then it's e to the power of, and then negative 0.97x, and then close these parentheses and close the other parentheses, and that should do it. Okay, that's pretty ugly. And then you can hit graph. So let's see, let's go to window. Let's choose from negative, I don't know, negative 10 to 10. And then the by ones, the output, let's go from negative 10 to, that's going to grow pretty quickly. So let's, I don't know, what does 1,000 look like? You can always come back and change this. And then go to graph, and there it goes, there it goes, there it goes, and boom, there's our general graph. Any questions about this? No? No? If I wanted to change the window, like maybe I want to see what happens over here, I want to go even bigger, then I'd have to go back to my window and change the y maximum to be something even bigger so I can see it. So 1,000 wasn't big enough. How about 10,000? 1, there's 10, 1, 2, 3. Enter. Graph. So now we see this, and wait a minute, look, it was growing, 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 but then it didn't keep growing forever. It kind of reached some sort of plateau max, and then we don't know what happened, right? So it cut off. And I don't really care what happens over here. Remember, t is the number is a time, so we don't want negative time. In this context here, we probably don't care about negative time. So let's go back to window. Let's change this from 0, let t start at 0. And let's go out further out. How about, let's make it twice as much. How about that? And also 10,000 turned out to be too big. How about we make it, I don't know, how about 6,000? Okay. So it goes up, it reaches some max, and then it kind of plateaus out. Okay. Good, 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 good. Okay. Studying this graph, why would that be? As the input grows bigger and bigger and bigger, this goes out toward infinity, this is going to get very, very large, bigger, 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 and bigger. As this gets bigger and bigger, bigger and bigger, then multiplying it by negative is going to grow toward negative infinity. So this is growing toward negative infinity times this number, e to the power of negative infinity. So this thing is growing toward 0. And so as this goes out to infinity, this is getting smaller and smaller and smaller and smaller. And so as it grows toward infinity, this is growing towards 0. 5 plus 0 equals to that, 5. So 5 divided by 10,000 is 2,000. So it looks like this is in a plateau around the 2,000 mark. So let's graph y equals to 2,000, and we'll see that. It kind of plateaus around there, around 2,000. Any questions about that? No? No? Let me write down what I said verbally on here. If you think about the limit, and maybe this might be new notation for some people, this is the limit as t grows toward infinity, right? As the function goes out to infinity, as the t value goes out to infinity, we want to explore what happens to v of t. That's what we want to do. Okay, so as t goes to infinity, then e to the power of, let's just start over here. I'm just kind of breaking it down. Negative 0.97 times t. Then as t goes out to positive infinity, it's getting bigger and bigger and bigger, multiplying a really big positive number times negative 0.97, this thing is going to head toward negative infinity. Good. And as this grows toward negative infinity, then e to the negative 0.97 times t, well then that's going to grow toward e to the power of negative infinity, which grows towards 0. Right? So as I plug in bigger and bigger numbers for t, this part will grow toward negative infinity, e to the negative infinity grows towards 0, and now as it gets closer and closer to 0, then the multiplication of a tiny little number close to 0 times 1245 is still going to grow towards 0. So 1245 times e to the power of negative 0.97t will also grow towards 0. Therefore, 5 plus 1245 times e to the negative 0.97t will grow toward 5. Right? This part will get smaller and smaller and smaller as t gets bigger and bigger. We contribute less and less to the addition of 5. Eventually, it's pretty close to just 5 by itself. And so as t goes to infinity, that division of 10,000 divided by this whole ugly thing, 5 plus 1245 e to the negative 0.97t, the whole thing just kind of grows toward 10,000 divided by 5, which is where we get the 2,000. Okay, so as t goes to infinity, this whole ugly fraction begins to approximate 2,000. This right here is the line y equals to 2,000. So this virus spreading through the population looks like it plateaus around 2,000 people out of the 10,000. So it looks like it's going to affect a maximum of 20% of the population, right, as t goes on to infinity. Why that is, I don't know. It's something special, particular about this virus. Maybe it has to do with the population itself. Maybe certain people are going to be immune to this virus, and so not everyone is going to be affected. Maybe this takes into account the resolutions that the city will take in order to prevent the virus. Who knows? There's all kinds of reasons, right? So we're not really explaining why that is. We're just coming up with an equation that seems to do a pretty good job of modeling the growth of a virus, right? Obviously, we're in the middle of coronavirus season, so we're working really hard to come up with equations that describe this sort of thing right now. How is this virus spreading through our world? And of course, it greatly varies from region to region. In some parts of the world, it's growing very, very quickly. And in some parts of the world, it's not growing very quickly at all. And that's due to a variety of reasons for why it's worse in some parts and not as bad in other parts. Some of it is, of course, due to genetics and population, the age of the population, and the health factor of the population, right? The virus will spread faster in a region with a bunch of sick people than it will in a section that has people that are very, very healthy and maybe naturally fight off the virus more. So it varies. And we're trying to come up with equations that model that as best we can, but the best we could do is an approximation, right? There's just too many variables, too many unknowns. It varies a lot from region to region. So we come up with general approximations that do a fairly good job overall. Okay, any questions? Good. Also, the shape of the growth is given by this graph. That's what's another thing that's really nice. We can see that at first it grew pretty fast. Well, it started off a little on the slow side as t went out to infinity, right? So at first it wasn't growing very quickly, and then it hit its stride, and then it grows really fast, really super fast. It's growing at a very fast rate around there. And then as we begin to approach its max of 20% of the population, it begins to slow down. There are less people that are susceptible to this virus until we slowly approach the 20% mark, and at some point we get to a point where no new growth will occur. Good. In terms of coronavirus and a virus growing into the population, that's what we call herd immunity, when there are no more people left for the virus to infect, and so we get to a point where the virus is like a hot potato getting passed from person to person to person to person. And when you get to a point where there isn't many new people in the population for the virus to infect, then as a herd, as a population, it found its immunity for the virus. So the virus then begins to die off since it doesn't have anybody new to infect. And the way to get to that will be to infect a bunch of people, and then those people either die, and if they survive, they have antibodies toward the virus, so they're less susceptible to getting the virus a second time. Some people are likely just going to be naturally immune to it. Their body will just fight it off. So there's people that are naturally immune to a virus. There are people that develop this immunity through antibodies. So they get sick, but then they recover and they have the antibody. Eventually, we'll figure out a vaccine for it. So some people will be vaccinated. But vaccines are usually not 100% or even close to it. So if we can, we're trying to aim for a goal of getting a vaccine that's approximately 50% effective. So if you get the vaccine, then the odds of you getting the virus when you're infected, when you're surrounded by someone who's infected, would be lowered. That's our goal. So even when you get the vaccine, you won't be 100% covered. It's not like you can get the vaccine and then you're like, aha, I'm cured. I can't get the disease, and now you can walk around and do whatever you want. That's not true. It'll lower the likelihood of you getting the disease, but it won't make it 100%. But the benefit of that is that it reduces, on the other side, the likelihood that the virus can spread. So you're just, again, removing the number of people, slowly reducing and removing the number of people that can get the virus in the population therefore slowly reaching that herd immunity and getting to a point where the virus has nowhere new to go, and then it dies off, right? It's like a fire, a forest fire going through the forest. It needs new trees every time to grow, right? Once it burns down that tree, the fire would burn down, except it needs to jump to a new tree, a new tree, a new tree. So the way we fight forest fires is not that we directly put out the fire. We don't have enough water for that. So what we do is we try and see where the fire line is heading, jump ahead of it, chop down all the trees ahead of it, and make a clearing so that the flames don't have a new place to go to, and then they kind of burn themselves out, right? So that's sort of the same idea here. We're trying to get to a point where we remove enough people from the population that are susceptible to the virus so that the virus has nowhere new to go to, right? And a vaccine will help in that fight. It'll remove some people. If it's only 50% effective, then it'll remove 50% of the people. That's half as many people that are now susceptible to the virus. Of course, there'll be a lot of people that refuse to take it. So even if we get a 50% effective vaccine, you gotta create it, disperse it, people have to take it. It might be a several-step process where you have to take it once and then 1 month later come back and take a second shot. And then, of course, some people will take the first shot and they won't come back for the second one. There's all kinds of complications that go into that. So it won't be like a one-shot clear and fix everything. It's something that helps us slow down the virus and get to a point where eventually it runs out of people and hopefully dies off. So anyway, I don't know. It's a random rant, but I figured it was applicable in our current environment. Any questions on anything? No? 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 Okay. Continuously compound interest. Remember that our formula for compound interest, we said that the formula was this guy. A of t, the balance at t years was equal to the principal invested, 1 plus r to the nth power, raised to the power of nt. It was like that, right? And so we thought, okay, what if n equals to 5, compounded 5 times per year? Well, let's not do 5. That's kind of an unusual number. If we make it equal to 12, that makes it monthly, right? So if we let n equal to 12, then this becomes a of t equals to p1 plus r divided by 12 to the power of 12 times t. And if we let n equal to 365, compounded monthly, compounded daily, this formula becomes this way. Right, so this is compounded monthly. Compounded monthly. This one's daily. Okay. What if we wanted more than that? What if we wanted it twice a day? Stop moving. Man, what's wrong with this computer? How about twice a day? I want to compound this twice a day, once at 6 a.m., once at 6 p.m. Twice a day. Well, in 1 year, it would be twice as much as this. So it'd be 365 times 2, 730 times it would get compounded in 1 year. So n would be equal to 730. And so the formula then would become a of t equals to p1 plus r over, oh man, why did this, you guys made me do it again, and we didn't say anything, I blame you. This is not 12, this is 365. So this is 730 here, raise the power of 730 times t. Good. Okay, well, we want to keep going. What happens? What happens as n grows? Not compounded twice a day. How about compounded 3 times a day? How many times will that be in a whole year? Compounded every hour, compounded every minute, compounded every second. We want to increase the number of times we compound until we get to infinity, and we want to explore what happens there. And so that's what this little algebraic manipulation here is doing. We're taking our original formula, right? Here's our formula, and we're thinking about what happens as n goes to infinity. But before we do that, it's useful to do this kind of a manipulation for it. And that's because, well, maybe an extra step would have been nice here. We have p, and we have 1 plus r over n raised to the power of nt. Okay, so here they're just introducing this result here, and you can just manipulate it because you can always multiply anything by 1. So let's multiply it by r over r, another version of 1. So that's fine. Okay. And so we can separate this in the following way. We can say that this is equivalent to p times 1 plus r over n to the power of n over r n over r. Keep my r red because my n's and my r's look very similar. So that's n over r times t r. Good. And that's what this is right there. Good. Okay, so then if we think about the relationship between these two, they're kind of opposite. This is r over n, this is n over r. So they just introduced a new variable. So let the new variable, m, equal to n over r. N over r. Good. Therefore, if we flip it around, that must mean that 1 over r, 1 over m, is then equal to r over n. Good. So now we can do this replacement, that r over n, right here, this is equal to 1 over m. 1 plus, right? And then n over r, that was the power of n. I hate this thing, why is it doing that? So then this is equal to n up here, n, right? N over r, times tr, right? And this whole thing is kind of separated like this. Good. Okay, so now we're going to explore what happens as n goes to infinity. As n heads out to infinity, as n becomes an infinitely large number, n goes out to infinity, then n divided by a constant, r, remember r is a constant, still goes out to infinity, right? Remembering that r is some given constant value, then that still goes out to infinity. So therefore m goes out to infinity. Good? Remember r is a constant. Right? So like the n value is getting bigger and bigger and bigger. It's 1,000, it's 1,000,000, it's 10 billion, it's 7 billion, it's 7 trillion, right? It's growing. And r is just some constant number. So let's say it's just 2. If you give me a number and a half it, okay, right? That's half as big. But that number is growing out to infinity, and half of infinity is still infinity, so it's still growing out of control, right? It's still growing toward infinity. Therefore, n is growing toward infinity, since it's defined as n over r, okay? And now this is exactly our formula for e. 1 plus 1 over m raised to the n power. As m goes to infinity, this will grow toward e. That was exactly the definition we had before, except before we had n instead of m. Same thing, m, n, it's just a dummy variable. So this process then leads you to have e. This whole thing leads to e raised to the power of tr. Good. So as n goes to infinity, this formula approaches e to the tr, or rt, and that's where this comes from, right over here. Right, so we do that little manipulation there, and we get that continuously compounded interest is given by this formula, p times e to the power of rt. Right? R is the interest rate per year, t is the number of years, p is the principal. Any questions? No? Okay, so here's an example. Find the amount after 3 years if $1,000 is invested at an interest rate of 12% per year, compounded continuously. So we saw what happened before when we invested $1,000 and compounded it every 3 months, compounded daily. So we saw what those results were before. But now if we want to compound it continuously, then the formula becomes this. A of t is equal to 1,000, the initial amount, e to the power of 3 times 0.12. Right? Another reason why e becomes so important, e helps us figure out continuously compound interest. Right? So it's key to a huge part of our financial infrastructure to use the letter e to model various equations in our economic system. 3 times 0.12, e to the power of that. And I get $1,433 $1,433.33 approximately. Do you guys get the same thing? Any questions? No? No? All right, let's take another little break and we'll get started on 4.3.